Well, hello there, Cave Physics Unit 2 student. We're going to work through the specimen paper from 2017. It's a Unit 2 paper 1, so this should be useful in helping you to prepare for your paper 1 exam that's coming up very quickly here, okay? So let's go down and start this question. So as usual, you have your list of physical constant on this page here. So now let's jump into the questions now and just work through them, okay? All right, so the first one, for the very first question, we have a 3-volt battery that causes a current of 0.5 amperes to flow along a wire for 4 seconds. What is the quantity of charge that passes in this time, right? So we're concerned with the quantity of charge that we get from this many volts, this many current, and this over this length of time, which is 4 seconds, right? So Q is equal to I times T is the formula that we should draw for immediately, right? We're working with a quantity of charge and we have time and current, so we can use this formula. And when we do that, we come out with Q is equal to 0.5 times 4, which is just 2, and the unit is coulomb. So we have C for our answer for number 1, okay? So moving on to number 2, they're saying that the energy per unit charge is a measure of what, right? If we have energy per unit charge, that's equivalent to our potential difference, right? So you might remember that the potential difference at a point is just the energy per unit charge there. And so we select D because this is the definition then of what potential difference is. So that's D for that answer. Now for question 3 is saying that there's a current of 0.25 amperes that flows in a uniform wire of length 2 meters, right? So we have a length 2 meters, current of 0.2 amperes is flowing along that length, and the cross-sectional area of that same wire is 2 times 10 to the negative 9 meters squared. And the potential difference when all of that is happening is 4.25 volts. So we're being asked to calculate the resistivity of the material from which the wire is made. So we know we're immediately going to pull for our resistivity formula, which can be related to the resistance, as resistance is equal to rho, which is our resistivity, times the length of that wire divided by the cross-sectional area of that said wire, right? So when we get this formula now, we just rearrange, making resistivity our subject. And so we end up with the resistivity being equal to RA divided by L. So all we have to do is plug in our values here. They gave us, they didn't give us a resistance, so we have to calculate that first and foremost from our current, and our from our voltage, and our current. So our voltage is 4.25, our current is 0.25. So when we divide those two out, we get our resistance, right? The resistance go in through that wire, and that's 17 ohms, right? And then all we have to do now is plug in for R is equal to 17. We know our cross-sectional area was 2 times 10 to the negative 9, and then divide that through by the length of the wire, which is 2 meters. And so when we do that, we come up with our resistivity being 1.7 times 10 to the negative 8 ohm meter, right? So remember, the units of resistivity is ohm meter. So that's what we get here when we do that, okay? So we just selected C. C is our answer in this case. So moving along to item 4, they're saying that item 4 refers to the following diagram, which shows an arrangement of electrical components in a circuit, right? So you see we have our variable resistor here. We also have a resistor here, and across that we have this voltmeter, and of course we have our source, right? So then moving up here, so the question is actually that the variable resistor is adjusted to provide a smaller resistance, right? So we are adjusting this variable resistor to provide a smaller resistance. So if the resistance here is small, right? So we have a small resistance. It's adjusted so that we have a small resistance there. Okay? So then the question is asking us now, which changes best describe the changes in the ammeter and voltmeter readings. So remember now, we have this ammeter in series, right, with our variable resistor. And so if there's a small resistance here, then there's going to be a lot of current. There's going to be an increase in the amount of current that's going through our ammeter, right? And by that same token, the voltmeter reading is also going to increase, right? So if our ammeter reading goes up, right, that means that our voltmeter also went up. So they're asking us to select the pairing that correlates to that. And so we select C, right? Our ammeter reading increased because we decreased the resistance flowing through that variable resistor. So we have more current flowing through. And then by that same token, we have an increase in our voltmeter reading as well, right? So C is our answer here. And so we're moving along to question 5. The cell in the following diagram has an EMF of 9.0 volts, right? So the cell has an EMF of 9.0 volts. And they're saying now that the reading on the high resistance voltmeter here, it's a high resistance voltmeter, it's here. And so what that's reading 5, right? That's reading 5 volts. So now they're asking, what is the current I? So essentially, what's the current flowing through this circuit is effectively what they're asking. And to do that, we can do V is equal to IR, so your regular Ohm's law. And so there's rearrange to make current the subject. So I is equal to V over R. But the key thing here is which voltage do we use, right? And we're going to use the 5.0 volt and not the 9 or any other value, because the reading on the voltmeter is 5. So we know that that is the effective voltage going through that circuit, right? So we use I is equal to 5 divided by that resistance, the total resistance of the circuit, which is 17 ohms. And we end up with the current that's flowing through the circuit being 5 over 17 amperes, right? So this is how we come up with our answer. We get C here, okay? All right, so moving along to question 6. Question 6 says that a 3-volt battery of negligible internal resistance is connected to 6 identical resistors as shown in the diagram below. So here's our 3-volt battery. We have 3 resistors here and we have 3 resistors here as well. They're all identical, right? So the question is asking, what is the potential difference between X and Y? So between this point here, right? Between this point here, what is my potential difference, right? So I'm trying to find the voltage across this here. So XY, VXY, let's call it VXY. Okay. So essentially what's happening here is that this, you can think of this as a potential divider, right? And so for potential dividers, we can find the voltage or the potential difference across any point by multiplying the total voltage coming in by the resistance of the load that's across that those points. So that would be R divided by the total resistance in that arm. So all these 3 resistors are in that arm down here. And so we would do the resistance of this particular load that's between that point divided by the total resistance, which would be what? R plus R plus R. So that's 3 R's, right? So we're going to do V, the potential difference across XY is going to be equal to the total voltage that's coming in multiplied by the resistance here divided by the total resistance in this arm, which is 3R. So when we do that, we get VT times R over 3R. We cancel these 2 R's with each other. And so we end up with VT is 3. So we plug that in. And so we end up with 3 times 1 over 3, and that's just 1 volt. So we come out with 1 volt being our potential difference, and we see that that's A here. So that's our correct answer, right, for number 6. So moving down to number 7 now. Number 7 is saying that in a closed circuit or loop, the algebraic sum of the EMF is equal to the algebraic sum of the products of current and resistance. Right? So this is Kirchhoff's second law, you might remember. And And so they're asking us which of the following statements down here is correct. So they're saying in the first case, they're saying this is Kirchhoff's first law, which is a consequence of conservation of energy. Now we know that that's not true. This is not Kirchhoff's first law. And even so, the first law is not based on conservation of energy, it's based on conservation of charge. So we can rule this one out. The second one says this is Kirchhoff's first law, which is a consequence of conservation of charge. This is not Kirchhoff's first law, it's his second law. So let's write that up here, first of all. It's a second law. So let's just be clear on that. It's Kirchhoff's second law, right? So that's Kirchhoff's second law. So we can rule out this as well because it is not the first law, it's the second law. So now we come down here and it says this is Kirchhoff's second law, which is a consequence of conservation of energy. And we're like, yep, that's our answer. This is correct. We don't even have to look any further, right? It's Kirchhoff's second law, which is a consequence of conservation of energy. And that's why we have the EMF being conserved, okay? So let's move on to question 8, which is this one up here. And it says item 8 refers to the following diagram, which shows a positive point charge in free space, right? So a positive point charge here, and then the distances from the charge to point X and to point Y are shown here. So this is our positive point charge. And the distance between it and X is R, the distance between it and Y is 4R. So the question is asking us, what is the ratio of the electric field strength at X to the ratio of the field strength at Y, right? So they're asking us the ratio of X to Y in terms of field strength. So what's our E at X and what would be our E at Y, right? So what is that ratio? That's what they're asking us to come up with. Now we know that this is the formula for field strength, right? When you have a point charge in the middle here, the electric field strength is equal to Q over 4 pi epsilon naught R squared, right? So they only gave us the distance here, so we can just kind of eliminate all of these other variables for now and just focus on our R, or R squared term, right? So in the case of X, right, the E would be effectively equal to 1 over R squared, right? Because it's a R here, and so we'd have 1 over R squared. And so for the Y, it would be 1 over 4R squared, right? Because remember, no, we're just looking at this R squared term in the bottom and relating that to our electric field strength. So for X, it's 1 over R squared. For Y, it's 1 over 4R squared, right? So that's the ratio that they're asking us about, X to Y. So this is X to Y, right? And so now we can simplify this even further. So we come over here and we have 1 over R squared. 1 over R squared, we can say that's equal to 1 over 16R squared, right? So then now if we want to find the ratio, what we're going to be doing then is dividing this 1 over R squared by 1 over 16R squared. And so when we do that whole rearrangement, what we end up getting is that 16R squared ends up being divided by R squared, and so we end up with our ratio being 16 to 1. Okay? So remember, the ratio they're asking us about is X to Y, and so we know what the field strength at X would be. It's 1 over R squared, and then we know what the field strength at Y would be. That's 1 over 4R squared. And so it's just a matter of simplification from here on out, and we end up with 16 to 1, right? So that's our answer here. And so moving along to question 9, question 9 reads that the force per unit charge, right, on a positive test charge placed at a point in a field is called, what is that the definition of? This is effectively the definition of electric field strength. So we just look for electric field strength and circle that one. That's D here, right? So again, the electric field strength is the force per unit charge on a positive test charge that's placed in an electric field, right? And so we know F over Q is our electric field strength, so we select D here. That's our answer. Moving right along. So here's question 10 now. So item 10 refers to the following diagram. So they're showing us this diagram now. We have point A here, and then we have this capacitor here, and then we have two capacitors here that are in parallel with each other. We have point B here, and down here we have another capacitor that's just chilling here that has a capacitance of C, right? So the question goes on to say each capacitor in the diagram above has capacitance C. So we can just write C here for every capacitor, right? What is the effective difference, the effective capacitance between A and B? So effectively, we're being asked to calculate the capacitance in this whole circuit, right? And so to do that, we're going to break down this question in three parts, right? For the first part, we're going to look at these two capacitors that are in parallel with each other, right? When you have parallel capacitors, you can just sum their capacitances. So we sum this C with this C, just straight up, a linear sum, and we end up with 2C. So this whole section here, let me put in another color, right? So this whole section of the diagram, we just simplify to be 2C, right? Because they're in parallel, so we just sum the two of them. Then what will happen now is we'll see that this 2C that we just calculated here is now in series with this C that's here. And so that's my second step here. When you have two capacitors in series, you just sum them. You sum them in this manner, right? So I would do 2C times C divided by 2C plus C. And so we end up getting 2C squared over 3C. And so this one of the C's cancel each other out, and we end up with 2 over 3C, right? So this whole part now, let me put in another color now. Put this in orange. This whole top part here now, right, is equal to 2 over 2/3 C, right? So now this top part is going to be in parallel with this bottom piece. And again, when we have two capacitors in parallel, we just simply do a linear sum of them, right? So that's what I did down here. We're just adding this 2/3 for this top part to the C that's down at the bottom because they're in parallel, and we can just do a simple linear sum. And when we do this, we come out with 5 over 3C. And that's C. That's C here. So that's how we ended up with this C, okay? So just remember, whenever you're faced with a diagram like this, just break it down into parts and then work your way to the final answer, pretty much like we did here. We broke down this parallel portion first, then we looked at the top part as a whole, right? And then we looked at the top part in comparison to the bottom, and then we just did our calculations accordingly, okay? So moving along to 11. So item 11 refers to the following diagram. And so we look at this diagram here, and what we see is that it's a solenoid, right? And you have your current flowing upward. So if you do your Fleming's right-hand rule and just wrap your 4 fingers around that solenoid, right? So take your right hand and wrap your 4 fingers around that coil. That's the direction of current, and that's what they're showing us. So we're just like hugging it. We're just wrapping our hands around it, right? 4 fingers around it. So a hollow solenoid, this solenoid has 100 turns in a length 0.5 meters, right? If a steady current of 2 amperes flows in the solenoid as shown in the diagram, so it's flowing in this direction, right? What is the magnitude and direction of the flux density in the middle? So you want to know the flux density in the middle of this coil, right? And so the formula for flux density when we're working with a coil of a certain number of turns and a length, we can use that the flux density B is equal to mu naught times the number of turns per length times the current that's flowing through that solenoid, right? So this is our go-to formula here. And so what we do next is we substitute in the values because we have all the values that we need to calculate B. So first we plug in our permittivity, right, of free space, and that's 4 pi times 10 to the -7. We multiply that by the number of turns, which is 100, divided by the length of that solenoid, which is 0.5, right? And then we multiply that by 2, which is the current that's flowing through the solenoid. And we come out with 5.0 times 10 to the -4 Teslas, okay? So this is the magnetic flux density. This is the value, the magnitude of it. And to find the direction, again, we're gonna take our right hand again and just wrap it around this coil in that same direction. So we're gonna have our 4 fingers wrapping around the coil, and what we'll see is that our thumb is gonna be pointing left, right? So that's the direction of the field lines, and so by extension, that's where the flux density will be felt, right? In that direction here. So it will be going left. Right, and so when we put this together, this magnitude together with the fact that it's going to the left, we come out with B as our answer. So that's how we get B, right? We have to use our Fleming's left-hand rule in this case to figure out the direction, right, to which the flux density will be felt. So moving down to 12. So for question 12, a wire of length 0.5 meters and resistance 5 ohms moves vertically with a velocity of 10 meters per second, perpendicular to a uniform magnetic field of flux density 4.0 times 10 to the negative 5 Tesla, right? What is the magnitude of the EMF, right? So we need to find the EMF that's generated between the ends of the wire. So this is an electromagnetic induction question, right? And so if we go back to that section of the syllabus, what we remember is that the formula for the induced EMF, right? Whenever you have a straight wire conductor that's moving with a particular velocity in a magnetic field, that formula for the EMF that's induced is equal to BL V, right? So make sure you remember this formula. EMF is equal to BLV, and we know B from the question is 4.0 times 10 to the negative 5. We know the length of the wire, that straight conductor, that's 0.5 meters, and we know that the velocity with which it's moving is 10. So all we have to do is just plug in these values here, and we come up with an EMF of 2.0 times 10 to the negative 4 volts. So that's how we ended up selecting B here for our answer, okay? All right, so moving along to question 30 now. An electron beam moving with speed V enters a uniform magnetic field acting down the page as shown. So this is our direction of our magnetic field. This is the electron beam is moving this way, so it's moving with that speed V in this direction. And so the question is asking, the beam of electrons will bend in which direction? Which direction will the beam of electrons bend? Okay, so here again is another case where we have to use our Fleming's right-hand rule, right? And so, well, actually, we're going to use Fleming's left-hand rule in this case, right? And so what we're going to do is we're going to take our left hand. The magnetic field is pointing down, so we're going to take our left hand, and we're going to take our index finger, right, our first finger, and we're going to just point that down. So take your index finger, point that downwards, right? Then now our second finger, which is our current finger, is supposed to be pointing to the left. So we're going to point our second finger to the left because it's an electron, and electrons are going to go in the opposite direction of conventional current. So because the electron is moving this way, we know the current must be going that way, right? So now what we have is we have our index finger, our first finger pointing downwards. We have our second finger pointing to the left. And then when we do our thumb, just stick out that thumb in the way that it will go now. And we see that that thumb is going to go out of the page, right? And so the beam of electrons will bend out of the page. So that's how we end up with A for our answer for 13, okay? So again, we're using Fleming's left-hand rule to figure out the direction of force, pretty much, is what we're finding, right? So how will that beam of electrons bend? It will bend out of the paper, right? Okay, so moving down to question 14. Question 14 here says, which diagram correctly shows the direction of forces acting on adjacent current-carrying conductors? So when we just kind of survey the answers here, we see that the current-carrying conductors that are adjacent to each other, here are pretty much carrying current in opposite directions, right? Current is flowing in opposite directions for these two adjacent current carrying conductors. And if current is flowing in opposite directions, we have to show one of these conductors being repelled by the other, right? And so we come down all the way to D, and that's what we show here. We see that this conductor is being repelled by this one, and that's because they're going in opposite directions, right? We can see that this current is going into the plane of the page, and this one is coming out. So because the current is going in opposite direction, we need to show repulsion, right? Because that's what happens in the case of a current flowing opposite to each other in those two different adjacent wires. Okay, so it would be a repulsion. So this is our answer for D here, for 14. So 14 is D. Okay, so moving down to question 15 now. The following diagrams illustrate a demonstration of Lenz's law of electromagnetic induction. In which of the diagram is the current in the correct direction? Right, so the current, what tells us the current direction is the pointer. Where's the pointer? On this galvanometer pointing. So we have to find the one that has the correct pairing of the magnet coming in contact with the solenoid and then the pointing of the galvanometer, right? And so if we look at the first one, we see that we have a south and a north here, right? And this magnet is being moved in and out of the solenoid, in and out of the solenoid here. That's how it's able to induce a current in it, right? And so Lenz's law, right? Lenz's law just says that the induced EMF that's generated, the current will move in such a way to oppose the change that causes that, right? To oppose whatever is causing that change. And so if we're moving in this magnet here and there's a north pole here, what's gonna happen is that the current is gonna flow in such a way to induce a north pole here, right? And a south pole here. So the current will flow to induce a north pole here that will repel this magnet and be like, get away from me, right? You're causing a change in me and I don't really want that. So let me just generate a like pole to you so that you will be repelled. So it generates a north pole here. And so if that happens, then what we have, right, is we have that this is the direction of our field, magnetic field is going to the left. And so if we use our Fleming's right-hand rule and just wrap around that coil, where is the current going, right? Where's our current gonna go? And the current should point to this direction. And so this is the correct answer, right? So we already started off with a bang. Part A is the answer. So we don't really have to go any further, right? But if we wanted to look at the second one, for example, we could do that, right? So let's look at this one. If this is coming nearby here, right? And we have our 4 fingers wrapped around the coil. That's the direction of current, right? Where would our poles be, right? What would each of our poles be? So this is basically saying that in this particular case, we have our current coming down like this. So that means that we have, what would we have? We have a south pole. Effectively, that means that we would have a south pole here and a north pole here, right? That's what this kind of setup tells us. And so if that's the case, that's not necessarily what we would need to happen, right? Because this is causing a change in the solenoid. We don't want a pole that's gonna attract it then. We would want something to repel it, and that's not what's formed in this case, right? Again, we can use our right-hand rule to figure out where what poles would be where, right, per this diagram. And so if we use our right hand and we point downwards, right, we're curving downwards because that's where the current is going, we'll see that our thumb points in the direction of field. And so this is telling us, this particular thing is telling us that the field lines would be going where. So the field lines in this particular case would be going this way, right? This way. Right? So we know that there would be a south pole here and there would be a north pole here, right? And so because of that, we know that this can't be right, right? This can't be right. But so that's the kind of analysis that you would need to do for these ones to figure out which one is wrong, right? If I'm coming in with a magnet, with a north pole here, and I'm like putting it in the solenoid, in and out, in and out, the solenoid is the current is gonna flow in such a way to resist that change, right? That induced EMF. And so it's gonna want to generate a north pole here and a south pole here. And when I curl my fingers, right, my right hand around that solenoid, what I get is that my field is pointing here when the current is like this. And so, and as we see on the galvanometer, it's pointing this way, which would indicate that the current is going opposite of this direction here to then generate that repulsion that's needed to be in alignment with Lenz's law. Okay, I hope that makes sense. If there are any questions about anything, definitely feel free to drop that in the comment section below. If this was helpful for you, definitely go ahead and let me know that as well. And again, please like and subscribe to the channel, share this video with your friends, and I'll see you in the next video.